I have so for 13 slide packs. Today I'll give you two of those. I guess you already have a series of lecture titles. Before starting this talk, I want to express my thanks to Dr. Vivek Dimoli. He's now out in the corridor, I guess. Actually, he prepared all of this lecture series process. And because I do not know the exact requirement this kind of lecture series wanted to have, so I asked him to communicate with the staff in this university, and he decided the final titles and raw materials of each slide. So I just slightly modify his the prepared slide. So some kind of case, I think it is a little bit deviated from my main focus, but I think all material, slide materials are fine to give a lecture. So first one is lecture 1, series lecture 1. Is about introduction to composite materials and their significance in various industries. So before starting this lecture series, so I just talk a very brief academic background of mine about composite, so that it can be helpful for you understand when you raise your questions and what can be expect more the professional answer from mine. Okay? So about composite, so it's a long time ago. So National University for my bachelor, my graduation thesis was about the design of a spiral heat exchanger. That means the thermal heat transfer, that is my one of major background. And for master degree in KAIST, Korea Advanced Institute of Science and Technology, there my master degree thesis was about the theory and the modeling of interface crack. So that means durability issue of composite material or the semiconductor packaging issue. So will be one of my main research focus. And the University of Michigan at Ann Arbor, when I got a PhD, so my thesis was about the mechanical behavior of ceramic matrix composites. At that time, my project sponsor was DuPont and Corning. So the high temperature use composite material.
This mic a little bit up. Voice is not audible.
Oh, okay. Now it's okay?
Now it's
okay. So that means among many composite materials, the ceramic matrix composites mainly used for the high temperatures. So at elevated temperature, maybe the composite material mechanics and its processing is one of my main research purpose. Right? And after that, during my sabbatical leave, I was in the Cornell University. At that time, I collaborated with the faculty about the mechanics of composites, so stress analysis, something like that. And after that, at the UCLA, their MEMS study was conducted, and that MEMS included the magnetostrictive materials. That means magnetostrictive material embedded composites can be used for intelligent switch composite something. That is my main the titles so far about composites. And so my main keyword can be said as mechanics and thermal stressing and composites. And to calculate and design composites, hand calculation is very minimal. It's not possible. That means for to use computational mechanics. So from my master degree days, I involved in programming to develop a finite element method. So far, in my laboratory, I programmed about 5 different the specialized finite element method program. Among 5, 2 of those are on the market these days in South Korea. So composite is very very vast concept. Actually, I can say all of material is composition. There is no pure material. Okay? But when we say a composite, that means artificially manufactured composite, rather than natural ones. So in that we can find the matrix terminology and reinforcement terminology. For reinforcement terminology, there's a particle or fiber, okay, fiber. Those terminologies can be found, right? So this case is automotive tire. So it is so generally we say steel wire reinforced rubber, but actually that matrix itself, not pure rubber. In that matrix is can be classified as another composite as matrix rubber and with carbon particles. Okay? So it's very difficult the subject to calculate the development actually. And fiber orientation in fiber reinforced composite is very important. So you can see that this is a mono directional the fiber reinforced composite. And this is also mono or directionally reinforced one, but the difference between two is this one is continuous fiber. It's used for reinforcement. This is discontinuous composite, discontinuous fiber is used to the reinforce the matrix. Right? And in this case, there is no preferred direction for reinforcement. It's randomly oriented. So in this case, usually we use chopped fibers. Chopped fiber, chopped fiber is used as reinforcement. So this is a discontinuous and randomly oriented fiber. Each one is one ply. So each ply can be stacked to make an overall structure. This is the case, the stacking and bonded from each plies. So to satisfy some designated purpose of structure, we can intentionally make its stacking sequence differently. Okay? It can be calculated for having the desired stiffness in spatial directions. So then, as a result, the benefit is it's well balanced, and the in-plane stiffness can be easily obtained as desired. And there is also a sandwich panel. Is one of common composite materials, especially for bending structure purpose. In the case of moment should be borne to bear external bending load. So as you see, the middle surface in the case, middle surface of composite is not good for bearing moment, as you see. So to make it lighter, we make a very light and the load bearing middle section is used. We say it is core. So honeycomb core is one of most the common shape for low density core. And the benefit is we can make a very highly moment bearing panel, but with very small weight and large bending stiffness can be obtained. So composite material means it has generally, we can say, reinforcement added into matrix, then composite can be outcome. So definition of composite material can be said combining two more distinct materials. So as a result, we wanted to create a material with properties superior to each component alone. Okay. So sometimes it feels like magic because very tough material can be synthesized from very brittle two different ceramics. Okay. So, and as a component matrix, so many times it's called as binder. So the binder is especially for PMC case as a matrix binder. So binder means it's just to hold the reinforcement together. It is not rolling for the supporting any the excessive load. So most of the load will be supported by reinforcement only in this case. So example include the resin and the metal can be matrix. It's a resin case polymer matrix composite. It is matrix, depth matrix resin, and the metal matrix composite. As metal is matrix. So matrix can be any material. And the reinforcement also, its purpose is to provide strength and stiffness. Example, the fiber, glass fiber or carbon fiber is very popular ones. And also ceramic particles can be used. Sometimes ceramic balls will be embedded into some aluminum matrix or something like that. So the key idea to develop any special composite materials is to get high strength to weight ratio. That's a very basic characteristic of desired composite. And we wanted to have the long-term durability and flexibility in design. Okay? Because flexibility in design means because composite design, composite material design includes specially intended directional stiffness, not all direction. So a combination of different constituents in composites can provide composite material the unique property which are different from individual constituents. So we can find the much better the property as a result. And so, although I said the composite consisted of reinforcement and matrix, but to evaluate its basic property of composite, there is one more characteristic must be focused. It is interface region because between matrix and fiber, that zone is interface. Interface characteristic, most of time it holds the life of that material. That means durability will be seriously influenced by interface characteristic. So interface characteristic mostly will be influenced by manufacturing process. So good manufacturing means take good care of interface. So that is very important for final composite material quality. Then the manufacturing is very, very important. And this department is industrial and production engineering. So that means manufacturing is one of the main purpose of this department. I believe that the manufacturing process among three different major regions for composite materials is most important. The three regions means material itself and the computational mechanics from mechanical engineering part to design structure, something like that, between the manufacturing. So these three specialties are very important. Among them, I can say, I wanted to say manufacturing is most important one. It decides the quality of marketing. Okay? So this is one of typical cross-section of unidirectional composite materials. There, between the blue circle means a fiber or cross-section, and the gray background is matrix, in this case resin. And between resin and the fiber, there's interface, the fiber matrix interface. This is very important. And also, so if there is too large matrix region, in the case, the composite quality will be degraded. So it must be cautioned. And reinforcement and layers. Layers, that means this is not a process in one the step. Usually it is a stacking, the manufacture through stacking, so each layer. So there are many, one layer, second layer, third layer, fourth layer. Okay? So each layer can make this kind of hand layer. There are many different kinds of manufacturing techniques. Among them, this is one of the examples. So we make an open mold, and on it resin. Resin is prepared. On that, the fiber will be distributed, and the resin, in the case, the many multiple layers can be prepared like this. Then after that, it is cured by using vacuum pack or top mold sometimes, and or hot pressing. There are many different kinds of manufacturing techniques. So this is for very typical the manufacturing process for composite material. The resin transfer molding, RTM, so-called RTM, and winding molding, and the autoclave molding, and the compression molding. This is four typical processes for making composite materials. Each manufacturing method has pros and cons, of course. So for RTM case, pro is very efficient, and is very strong for pollution, against pollution, and the adaptability is very excellent. But during its processing characteristic, it can make much more air pockets. So high porosity can exist, and the controllability accordingly very low. And the winding process means its shape is limited to tubular type, and the productivity is very good because it can be automated. The reliability is very good, but cost is very high, and adaptability. For example, Inha University is owned by Korean Air. Okay. The Korean Air provide the flight service, but also it has manufacturing industry. So when I visited the Korean Air manufacturing plant, I can see the huge size of the winding machine. I heard it is 50 million US dollar. So for one machine, so it's very expensive. Right. So so we will discuss later. Today we will just see the very introductory level only, right? So autoclave or molding is it has a large, it can cure the large part. So the at that factory, when I visited there also one of the tail wing for airplane was autoclaved. So that means that autoclave size is 20 meter high. So it's very big. The autoclave can be properly working. So that means a large part can be cured properly, and very low porosity accordingly possible, and part of stability, property stability can be expected. But energy consumption is too high because it has a huge inner space to cure. That means heating and cooling, the energy consumption is too high. And that means cost is very high. And the compression molding case, the cost is very low, and low internal stress because it's very similar to the steel plate compression. So it's very traditional process, but infiltration effect is difficult. Preparation efficiency is very low. And so actually, composite material is not so. Sorry, composite material is not new material. Actually, it is one of very old materials. So it's going back to the ancient times, in Egyptian time, something like this. So we can find all of composite material, the characteristic structures from natural ones and ancient pottery, something like that. But we say in the 1960s, we got to know composite materials is very important to industrial application, because in those days there was a reason the world could develop this kind of technology greatly, because there was big the scientific technological battle between Soviet Union and the United States for spaceship. So at that time, to launch a very strong but very light the space structure, the composite material should be used. So that means the calculation for design is not possible by hand. So United States developed source code of calculation, so-called finite element method code, for free to the many organizations in the United States. That source code name is Nestran. So Nestran was a free code to the organization in the United States. These days, just some of companies, organizations, evolved that raw program for commercialization. So MSC is one of our company name, Ambedkar Corporation, something like that. It is in Seattle, Washington State, near Boeing company. So it's conducted many projects with Boeing, and that program was developed more advanced based on the original the Nestran. So we say it is MSC Nestran. So we can see those kind of the excellent commercialized computational tool these days. So that's origin is start from the 1960s. Okay. So in 1960s, there was a significant advancement in the development of composite material. Okay. And the carbon fiber and the new manufacturing techniques developed. As a result, the composite material been, we can say it's started at those days. But historically, it's 7,000 years ago. But the why intelligent and the advanced composite needed to be developed, because conventionally here, this horizontal line is a specific strength. So, and this vertical is a specific modulus. That means a high Young's modulus line, this one, the high stiffness can be hold. Right? So this metals, this metal group. So this is a weaker and light ones forms. But this lighter one, but higher strength can be found in this group. This group is beyond the metals. And this part is the CF part, the carbon fiber reinforced polymer, CFRP. This is one of the most prevailing and important composite these days. This is composite group we are using these days. We say this group as advanced composite, but just the composite material, as it can be found from natural ones to ancient ones, and even the traditional local houses made of composite, like the clay reinforced by some plants. Some plants can be used for reinforcement for building house in the traditional AC. And this polymer level. So this kind of build-up is very benefit to design composite materials. So this is very famous. This commercialized chart by HB. It's Oxford University. Cambridge, I'm not so sure this name, but the one famous professor from UK, he developed this kind of chart, the research, and he commercialized these days this kind of the chart. This why this kind of chart is very important to design composite, because we can choose fibers and the matrix as we wish it. And also this is just a constant temperature case, but if you pay for those information, in that case you can find many different level of temperature. The properties can be chosen, of course.
What is this technical and non-technical composites?
This one?
Here you have written non-technical ceramics and technical ceramics.
This one. This
I'm not from ceramic background. I just want to know what is this ceramics, technical ceramics and non-technical ceramics.
this is fine ceramics. This is the conventional ceramics. So fine ceramics, that means it's more the fine particles before sintering.
And the composite part that we are referring to over here, this confers to FRPs, or this also includes CMCs and MMCs?
So MMC, I guess the MMC is maybe, I guess this part MMC, I guess. And FRP may polymer based one around here, I guess. Yes. This is,
This composite picture is covering all the three.
yeah. Just the conceptual.
I'm just comparing that strength part, the metals and the FRPs and CMCs.
And so composite industry, its growth rate is enormous. So all of the terminologies and technology sectors that I will introduce a series of lecturing, any one of those can be great business if you concentrate. Because there is no the saturated composite technology at all in composite materials, including manufacturing process, because still fully automation is not possible. So all of the points can be good start point for new business. So this 2018, 2019, 2020, up to here, because this is the documentation from 2023. So maybe up to here, that is the identified one, real one. That's the expected one, extended forecast one. So, but overall, its growth rate is 12% per year. It's enormous because 7% growth means in 10 years its market doubled. This is 12%. That means 6 or 7 years the market size will be doubled. This is current the trend, but it will be accelerated. So any of technique needed in composite materials can be great business start points, even these days. Okay? So these blue ones is North American proportion, and orange block European proportion, and the gray ones Asian Pacific, and yellow is South America, and Middle East and Africa is the blue ones, top ones. So that is current market. And composite is it have a particular strength and weaknesses very less. I think weakness, or it has weakness, but its weakness is very narrow, I think, and which should be considered at the specifying stage. The composites are no means of the right material for every. That is what we must keep in mind when we wanted to use composite material for any application, but major driving force behind it is a combination of reinforcement and the matrix. That combination is a pair of fiber or reinforcement type or matrix, those kind. It's a combination is enormously huge. So if you can choose the right pair, then it's, and of course it must be well manufactured. So in the laboratory it's very easy to make the specimen manufacturing, although it is expensive. But its volume is large, it's different story. It's very difficult. But if you can choose the right pair, in the case that performance is enormous. It cannot be compatible with existing materials. It's a very attractive point to be involved in composite material business sector. So if you want any required final property of material, this is composite material, including the monolithic materials. So composite material can be synthesized by yourself, if you can make, It's very attractive point. So it's very challenging, but very desirable to try, I guess. For example, if a final composite needs to be fire resistant, so it's very difficult to find from natural material, but fire resistant and some level of stiffness and any kind of, but you can synthesize by yourself through composite materials. Okay? Fire resistant matrix. There are many fire resistant natural monolithic materials like ceramic. Okay? But the ceramic cannot be used as for that purpose, as it is, because it's brittle. But it can be toughened by using reinforcement. So you can create new ones. Okay. So in the 50 years ago, if we think of airplane, everybody think aluminum alloy or duralumin, something like that. That's all. But these days, everybody think, especially he is in the airplane manufacturer or the designer, then everybody think composites. So it changed from 10 years ago, due to Airbus. And this is a Boeing 787 body. Okay? Among whole materials, the half of it composite only. Half of it. And still 10% aluminum, only 20%. It's a great change from many decades ago. So what is great contribution from Airbus 10 years ago? Because before that time, the airplane manufacturers never use composite as a primary structure material, because its manufacturing is so costly and its maintenance is very difficult. So, but because it is very light, lighter than aluminum and cheaper than aluminum, in some cases PNC. So those materials were used even before that time for secondary structure purpose, the interior of the airplane. But Airbus started to use very challenging of glare composites for its primary structure. So that made Airbus possible to make a huge aircraft is Airbus. So that was big change in airplane market. And composite is very important in airplane. Composite used aerospace structure advantage, very light and high fatigue resistance. So aluminum is very less durable. It is aluminum every time it is deteriorated due to fatigue. Aluminum cannot sustain at even at very low stress range, because aluminum the SA curve has no limit, as you see. So it's a slow, it's a decline. So after 2 million, 3 million, eventually 10 million, it will fracture finally. But still has its limit. If it is very low stress range, the steel never, still will not fracture at all if it is very low stress range. So differently from steel, aluminum has great the weakness in durability. But composite material is a high fatigue resistance is very possible. And the fire resistance high, and the corrosion is very important, right? Its corrosion resistance is very high. Aluminum is very weak to corrosion. Right? And composite can produce in complex sheet because it is synthesized artificially. And most ironically, is mostly the man-made work is needed. That means it's expensive. So fully automatic is not made yet. So, but due to that kind of process characteristic, complex shape is possible, and a large piece also possible because it is man-made. Process is included. Okay? Disadvantage is very expensive, and the strength property is not equal in all directions. And so it's a reinforcement material direction is affect the performance, and the maintenance is very difficult, and material quality depending on production, and no standard quality. So it must be overcome. And the materials constituent materials along with a process by which they are combined determine properties of finished complete part. So that means there are many choices among fibers. So here is we are talking about just advanced fiber only, not conventional fiber. So advanced fiber is E-glass is most the common ones, the cheap one, common ones, and the carbon fiber and the aramid fiber, natural fibers is increasing to be used these days. Anyway, because recycle issue. So these fibers, advanced fiber means it's the dimension issue. The diameter of any material, if the diameter, it's a fiber type, if you think kind of cylindrical shape, if you can make as thin as you can, that means the smaller diameter, the higher stiffness. For example, this glass is the same as conventional glass, but conventional glass, it cannot resist up to 20 megapascal. It breaks away. But if you make it very thin, very small dimension, conventional e-glass is 100 micrometer, but these days e-glass is about 30 to 50 micrometer. So 30 to 50 micrometer means your hair, its diameter about 50 micrometer. So that amount of e-glass, its strength is more than 1 gigapascal. That means it's greatly increased if you can make in a small dimension, because that means it is because if you make a very small dimension, that means in small dimension, large defect cannot be included. That's why it is highly stressed. The very bulk glass, there can be huge, the big, the air pocket can be included, for example. It is kind of crack. But if you can make smaller and smaller, then the big porosity cannot be included, because in the processing, it is just failed. So you cannot produce. So that's why fibers, advanced fibers are very, so, what? Can you hear? Okay. Pore size. So I have to go faster. The carbon fiber is less than 10 micron. So 5 microns also in diameter. And if it is viscose type, very very short fiber, we will say it is viscose. Viscose is just 2 micron or 1 micron in diameter. So that's why it is very strong, very strong. So, so there are so many different type of advanced fibers these days. That means you can have freedom to choose one of those for your design purpose. And the resin is the one of polymers, long chain like molecules. There are some of plastic, some of sets. Those kind of resins are existing, and if the glass fiber is reinforced, then we say it's a glass fiber reinforced polymer, GFRP. If carbon is reinforced, then carbon fiber reinforced polymer, CFRP. And etc. We need to use a filler or additives, not just a matrix and a fiber. For processing purpose or some kind of stability of performance, we need to add filler or additives in addition. And there is intermediate materials. So this is a little bit a detailed part of manufacturing included, not just the big aspect of reinforcement matrix only. There are more materials needed at a time, and some technique is needed. Then the reinforcement. So not just one directional or long fiber or discontinuous fiber. If it wanted to be shaped in 3-dimensional or something like that, in the case you can make a 3D preform, like making your sweater. So you can make it's the same technique is used for making sweater, the cloth. So by using advanced fibers, so you can make 3-dimensional the structures, and in the process, that the free form will be the wetted in the resin. So it's a kind of process. Anyway, the 3D freeform can be used, and this one is a carbon fiber impregnated with resin. That kind of form is, we say, is a prepreg. Prepreg is looks like a tape, just the 3M tape. It is the prepreg. It can be used as a raw or material form to make special shaped composite material. And the BMC terminology. BMC is a bulk moduling compound. So this is a mixture of short chopped fiber, resin, and the filler used in injection. So that is BMC, and also SMC. SMC is a sheet molding compound. Okay. This is intermediate material. That means it is not very basic material, not a final composite material. It's between intermediate level materials. Okay. And also there is a thermoplastic preparator can be purchased on the market to make your own composite materials. And the benefits to use those kind of material, mid intermediate or so original fiber matrix, various kinds of material shape can be used for composite material processing. The benefit, durability maintenance, and added functionality can be adopted as you wish. Okay? And the design freedom is guaranteed. Okay? Using composite material, there are some challenges. Because the one most worrisome is cost. It's expensive. Okay? Composite material can be more expensive than traditional material. It's much more expensive than traditional material. This is because reinforcement in composite material is often made of high-cost material. Not just that. The cost is okay. That can be covered. But the problem is manufacturing cost is so high. So that means if you can invent good manufacturing method, then it is enormous business. Still, it is being tried. So RTM, so there are also ITM processor. Because every kind of modification manufacturing method is patented. So if your developed method can be adopted by big manufacturing company, then every daily they will pay you for your idea. Okay? So it is impossible at the desk. You and the testing as result. It can. It is needed to develop new manufacturing cost. Anyway, cost is manufacturing is the main contributor, and the sensitivity to moisture. That means corrosion is no problem, but the sensitivity to moisture. This is the case of polymer matrix. Polymer is very weak to moisture, and barrier is limited to PMC, and so this is brittleness. B is missing, brittleness, and the manufacturing complexity. So manufacturing is difficult. That means, and the advantage lightweight, corrosion resistance, high impact resistance, thermal. That we need material like the good thermal conductivity, but bad, poor electrical conductivity. Sometimes we need low thermal conductivity but high electrical conductivity. For example, if you think LED light sink, the heat sink, in the case of mostly we use aluminum alloy. Because it is lighter and as a heat sink, it has very high thermal conductivity. Right? But the problem is it is very good electrical, very good electrical conductivity. Very good electric conductor. That means so aluminum can so you can get some kind of electric shock when you touch it. So if that heat sink is good, very excellent thermal conductivity, thermal conductor, but very poor electrical conductor, that means it will be very good heat sink. It's very important even for micro scale, the chip industry. Okay, so that is those kind of material inventor and patented materials. Very, very expensive. But if you can make it based on nanoparticle based composite material, you can do. Then in the case it will be very nice. For example, if it's a very poor thermal conductivity but very good temperature, very good electrical conductor, in the case very few, 4% of carbon nanotube can be used together with the resin. In the case it will be very good electric conductor but very poor thermal conductor, something like that. Anyway, some kind of combination very important for material design and applications. So application can be found everywhere, especially aerospace, automotive, construction. So there's massively the consumer of composite materials. So as I said before, the aerospace is one of main material already. So lightweight, durable, for fuel efficient, something like that. And the automotive case also, because it can improve fuel efficiency. So it is becoming one of the main properties, the main materials becoming, not the completely one. Because so far you can find just a small number of parts made of composite materials for automotives, except very expensive parts. But steel, aluminum, now it is converting to the composite materials for automotive parts. So BMW i3 electric vehicle with carbon fiber reinforced plastic. Also it is expensive, but BMW car is it can cover the cost of carbon fiber reinforced plastic. If it is cheap car, it cannot use CFRP, but if it can sell at just a few slides. And the construction is better. The lightweight is not important, but durable and corrosion resistant is very important for construction. And renewable energy part, wind turbine blade, electronic, sports goods, and space So it's very widely adopting composite materials as the main materials. In the aerospace case, it can be break down into many parts. Each of the detailed sector use different composite materials. It's not one type of composite material. So aircraft structure and the fuselage and the wings and the tail fin and the door bearing, rotor blade, jet engine components, all of parts use different type of composite materials. But mainly they are adopting composite materials for their materials. The automotive part is the interior application, dashboard, console, seat and trim already, and exterior parts, body panel, bumper, aerodynamics purpose. And the structural components, chassis frame, crash worthiness purpose. And the thermal acoustic insulation, powertrain components, EV battery includes so far. So on. And the construction parts, cladding, facades, roofing, insulation, corrosion resistant structure, prefabricated composite panel, utility pole and structural support bridge deck. The renewable energy, wind energy, turbine blade, solar energy, hydropower, wave and tidal energy, geothermal energy, piping, casting. So there are so many different kinds of, but for example, turbine blade, I involved in the turbine blade development for aircraft for 3 years. For serious, based on ceramic matrix composite. So that means I just engaged the recent years, 3 years to develop a turbine blade, but there is companies to develop turbine blades for their business for 20 years, 30 years. That means what I mean is even one of part can be your lifetime business issue. So design method, manufacturing method, and the final dimensioning finish, is everything is very important for each industry. The electronics is a PCB and heat sink and the thermal management problem issue, and the enclosure and casing, and the battery housing, energy storage, and antenna signal transmission components, display wearable technology. For example, antenna itself is one company near in Han University in South Korea. So they are making a revenue $0.5 billion a year, just the antenna. As composite materials. So you can study all of those at a time. You don't need to do that. You can focus on just one of those if you have great interest. Then you can focus on one of those. If you can contribute, then you can make great money. So this is our last slide of the lecture one. So the future trend and innovation in composites is differently from today. The recyclability is very important issue these days. So if you develop a new composite system, in the case, many times you will be asked how about to recycle that material. So that recyclability is one of the future issues. And another one is smart composite. So that means that composite, that material is a live one. So that means like a skin. It can sense it can actuate, the sensor and the actuator can be embedded into the the materials. So smart composite is another issue. And the self-healing composite, that means if there is a micro-scale damage occurred, then self-cured. It's especially for bridge construction in the civil engineering. They are finding those kind of things or building materials. And the sustainable materials. So biocomposite like a plant fiber reinforced material for eco-friendly solution, those kind of things are these days and the future issue for new composite materials. So this is about the introduction to composite materials. So after this lecture, we will try to see the one by one. Although those are another large scope, but I wanted to introduce you how composite material is important in these days industries, and so why you are studying it in the university, because you wanted to make the good money and have good technology. That technology can support your lifetime. Yes. So you must have some direction. What should I spend my time, my valuable time? In that case, I strongly recommend you to choose one of those terminologies. Then you can find your way, because it is just a starting point, not a saturated point. So let's go together with me through the 10 more lectures to see what kind of issues existing in composite materials. Right? Okay, this is the end of that one. Do you have any question or suggestion? Sorry about the poor microphone. Usually I don't use a microphone when I give a lecture. It's not familiar with me. If you don't have any, you have?
On what basis we are classifying the part fiber composite and non-composite, like continuous composite? And like we have a 2-meter width structure, and we are putting half meter of fiber, half meter length of fiber in that part. So we will call it as a continuous composite, or we will call it a
I did not see that kind of case because the long continuous fiber is used to chopped fiber used is just decided, because depending on its the part size already. So it looks like a fault point, not intentional point. So I mean, if you want to make a 2-meter structure, then you never use the half length of fiber into one component.
There is any ratio on that basis we can define that, okay, we will call it as a continuous composite, or we will call it as a short fiber composite?
Must say with raw materials. If you use as an ingredient chopped fiber, in the case it is chopped fiber reinforced composite material. Yeah. If you are very long fiber, it has kind of a winding already. So in the process, when you pull that long fiber all the time, then it's a long fiber reinforced composite. Something like that. So this continuous one is different from chopped fiber. This continuous one is must be aligned differently from chopped fiber ones. in the case of well aligned, but its original raw material is already chopped. So because it's a long fiber is prepared, but during manufacture it's chopped. It's chopped. It's continuously. Although its alignment is very
This also depends on the component part that we are manufacturing. Like if we manufacture a part that is
correct.
like the size of this room,
Yeah.
then the length of the fiber is very much short and we can define it as a short fiber. But if the fibers are made according to the whole length of the composite part, then we say it as a long fiber. Another question is that you said that complex structures can be made through the composite manufacturing. But if we will see the traditional composite manufacturing process, then it is very difficult for us to get the composite part. Either if we will get the complex composite, if we want to manufacture complex composite, then we will have to do the post processing. After the manufacturing of composite panel, we will have to do the post processing, and that is very difficult to do in the composite. So how we can
The reason is complex shape can be made of the composite material. So I said it's kind of man-made, manual work is needed, right, for processing the composite. So the mold is prepared. So any kind of shape we wanted to have, and then so very complicated, complex shape can be prepared, right, as a mold. Then manual work will be done on it, okay, not by the fully automated machine. Okay. By semi-automatic machine is needed to do some work on it. So any kind of shape can be accomplished. So that means, yeah, so that's why it's expensive. So that's why I said this ironically. Ironically.
The properties are different directions for composite material. It's anisotropic. So it was known from 1930 onwards, composite materials are there, but still the researchers are they're solving how can we improve this anisotropic or composite materials?
Isotropic composite materials.
Yeah, these different properties in different directions now. That is a major disadvantage for composite materials.
So the randomly oriented one, it's isotropic property after all. Right? So the purpose of that kind of composite material is the target is different. Not specific directional the high stiffness is not target. It is overall property. It's corrosion resistant to the weight, lightweight, but the reasonable stiffness in the case. So if you cannot find appropriate monolithic material for your purpose, in that case you can mix it, not for the specific directional stiffness. In the case, randomly oriented one is needed, and its effective isotropic property can be easily calculated from mechanical engineering. Even the computation program support you is very easy. Okay, so let's see the next lecture. Okay, so, all right, thank you so much.